Hello, we're going to talk today about the heat equation, which is also known as the conduction equation. The goal here is to try to find the temperature distribution in a solid. So we're going to apply the first law locally over this tiny, what we call infinitesimal control volume, which has dimensions of dx, dy, and dz. So to do that, we're going to start with the first law. Now here in this version of the first law, I've expanded the heat generation or heat transfer term, the capital Q dot, into a heat flux term along the surface and a heat generation term in the volume. So we're going to start from this basic equation. We're going to make some assumptions. We're going to assume we're working with a solid, so there's not going to be any flow. We're also going to neglect the work terms because we only care about heat transfer for this particular application. So then we're going to convert the d volumes into a dx, dy, dz, and we're going to assume that the heat generation term and the internal energy and the density are constant over this small tiny volume. And when we do that, we can eliminate the integrals on these two terms and rewrite the equation this way. So now we have to look at this heat flux term. And the way we're going to do that is we're going to rewrite that by expanding it. Instead of having this integral, we're just going to use heat in and heat out. So we're going to take the heat in through this side times this area, and we're going to subtract the heat out through this side from this area. And so we're going to end up with qx minus qx plus delta x times the area, which is delta y times delta z. And we're going to do this for all three coordinate directions. And when we do that and substitute in to our equation, we can combine all of this and then divide through by delta x, delta y, delta z to get the q dot and the internal energy term by themselves. So once we've done that, we have a delta q over a delta x, a delta q over delta y, a delta q over delta z, so we can convert those into derivatives. And so this becomes sort of a fundamental description of the first law of thermodynamics at a local point. So then what we're going to do is substitute Fourier's law of conduction. So we're going to convert the heat flux to thermal conductivity times gradient of temperature. And this is going to be the typical version of the heat equation. Now we can make some assumptions here. We can assume that the thermal conductivity is constant, so it'll come out from that gradient term. And we can also assume that du is going to be specific heat times dt. So if we make those two substitutions, we get this version of the heat equation, which is pretty common. And then we can divide through by the thermal conductivity K. And that gives us this version, and we can convert this K over rho Cp here to thermal diffusivity alpha. And this is a very common version of the heat equation, and it's the one we'll work with for the most part. There are some key simplifications here. If the time derivative is 0, we have a steady state problem. If it's non-zero, then we have a transient or unsteady problem. We can also have problems where the gradient term only has dependence on one coordinate direction, like x. So that would be a one-dimensional problem. If it depends on two directions, like x and y, then it's two-dimensional. And if it depends on all three, then it's a three-dimensional problem. We can also use Cartesian, cylindrical, or spherical coordinates for this equation. So if it's a steady state problem, this time derivative becomes 0. If there's no heat generation in the problem, then this term can become 0. And if there's no heat generation and steady state, it reduces to essentially Laplace's equation, del squared t equals 0, which we've studied very extensively in history. Now we can also look at this equation in our cylindrical coordinate system. You can see the gradient term becomes a little bit complex, but still reasonable. And we can also look at the cylindrical coordinates for solving problems involving cylindrical geometries. Now, the question then is, how can we use the conduction rate equation in combination with the heat equation? And we do that to find the heat rate, the heat fluxes. Once we know the temperature distribution, we can use Fourier's law to find the heat fluxes or the heat transfer rates. However, in order to use this, the thermal conductivity has to be known. The thermal conductivity is a transport property, and it determines the rate of energy transfer by diffusion. It depends pretty strongly on the physical structure of the material, the state, the crystal structure, grain boundaries, and so on. And it's really defined from Fourier's law like this. So when we're trying to find thermal conductivity, we actually perform experiments where we measure heat flux and we measure temperature gradient, and we use that to find the thermal conductivity. Now, for a material that's isotropic, the thermal conductivity is the same in the x, y, and z directions. And most problems are going to involve isotropic materials, but not all materials are isotropic. A good example is graphite, which has a preferential direction for the highest thermal conductivity. So this is our definition of thermal conductivity. We have to know the thermal conductivity in order to use Fourier's law of conduction to get heat fluxes. And this graph just kind of shows some common ranges for thermal conductivities for various types of substances. Gold and silver, you can see here, have very high conductivity. And in addition, especially gold is very soft, so it can create a more robust contact between surfaces. This is actually why gold-plated connectors are used on high-end audio-video equipment. It produces a more stable, high-conductivity connection. Now, in solids, thermal transport is due to the motion of electrons and lattice vibrations or phonons. In liquids or gases, we get our thermal conductivity from the kinetic theory of gases. Turns out it's generally independent of pressure, but it does depend very strongly on temperature. So when solving problems, we have to be very careful what value of the thermal conductivity we use. If we have a large temperature range, we have to choose an appropriate average thermal conductivity. So in solids, we typically see thermal conductivities decrease with temperature because of interference due to the vibrations themselves. However, there are exceptions. For instance, if you look here, fused quartz, the thermal conductivity increases with temperatures. Iron has an iron or aluminum oxide here decreases and then eventually increases with temperature. So there are exceptions, and it's mostly recommended to rely on tabulated values. And here you can see with liquids, again, liquids we typically see reductions with temperature, but there are some notable exceptions, water and glycerin and so on. So if we look at insulators, thermal insulations are mixtures of materials which are designed to achieve a very low system heat transfer. Now, industry uses the R value. The R value is thickness over effective thermal conductivity. And then there's also a different version of R, which is 1 over the effective thermal conductivity. So these are typically a mixture of some solid, like fiberglass, with an air or a vacuum. Fibrous insulations have small particles or fibers. They're very porous. Cellular insulations have small open or closed cells. They're usually in the form of boards, but they can also be foamed or sprayed in place, so that spray-on insulation is an example of cellular insulation. They tend to be very low density and low heat capacity and have good compressive strength. Granular insulations have small particles of inorganic materials. So there's a whole bunch of different kinds. You can see here some cellular. These are the kind of like granular particles or organic materials. And here's just some different examples of microscopically what these systems look like. Now, R values are typically given in English units, foot squared Fahrenheit per BTU per second. It measures the heat transfer per unit area for a given temperature difference. But that Rin is a value that's provided on a per inch basis to give the resistance per inch of insulation thickness. We also need boundary and initial conditions for problems with the heat equation. So we need an initial condition, but we only need one because the problem is first order in time. However, we need 2 boundary conditions for each coordinate direction because of that second order derivative. So the initial condition specifies the condition at a particular time, and the boundary conditions specify the behaviors at the edges of the problem. Now there's 3 major types of boundary conditions. Dirichlet is a constant temperature boundary condition. For instance, a surface that's in contact with something that's melting or boiling. So just we define the temperature on the boundary. The Newman boundary is a constant heat flux surface. So it specifies the temperature gradient or the first derivative at the boundary. So this could be something like an electrical heater or an insulated surface which has no heat transfer, which means temperature gradient is 0 at the surface for an insulated surface. Or we can have a mixed boundary condition. This is, for an example, is a convection condition where the heat flux at the surface, negative K dt dx, is going to be equal to the convection coefficient times some temperature difference. And this is actually a mixture of constant surface temperature and constant surface heat flux, which is why it's called a mixed boundary condition.